Ever thought how math seems messy and random? If it's yes, it's ideal to study it with a systematic framework. The framework may or may not exist elsewhere. That doesn't matter. What matters here is results and how we feel while working toward them. Here's another logically systematic way to approach mathematics. I'll discuss the best ways to approach math, regardless of whether it's pure, applied, or something else. Let this be mathmap underscore v.1, flexible for future updates, explaining the core pillars along which everything revolves. Core pillars along which everything revolves. Mathematical domains and domain hybridics, mathematical representation, mathematical concepts, manipulation, problems. Now we discuss each pillar one by one. This is part one of the project to build a systematic framework to approach mathematics. The lists below are not ranked, they're organized. 1. Mathematical domains and domain hybridics. Mathematical domains consist of areas like algebra, number theory, geometry, analysis, arithmetic, combinatorics, probability, and statistics, etc. Domain hybridics, two kinds. Hybridics within mathematics, intersections that mix mathematical domains. Examples: coordinate geometry, algebra plus geometry, calculus, analysis plus geometry plus algebra, linear algebra, algebra plus geometry plus systems theory, etc. Cross-disciplinary hybridics, math connecting to other subjects. Examples: cryptography, number theory, plus algebra, plus computer science, machine learning, probability, plus linear algebra, plus optimization, plus computer science, computer graphics, geometry, plus linear algebra, plus numerical methods, and so on. 2. Mathematical representation. Representation is how we encode and visualize mathematical ideas, symbols, notation, diagrams, graphs, equations, matrices, and proof structure, etc. Notation systems, variables, operators, quantifiers, index notation, etc. Visual representations, plots, geometric diagrams, phase portraits, vector fields, etc. Proof writing, a hybrid of representation and logical reasoning. Design choices, how you choose an equation, coordinate system, or diagram, changes what is easy to manipulate and what is hard to see. Example in plain words: for motion, write equals u times t plus 1 half times a times t squared. Symbols represent quantities, algebra encodes relations, graphs visualize behavior, and units / notation keep the representation precise. 3. Mathematical concepts. Concepts equals theories, theorems, postulates, rules, laws, definitions, and so on. Major and widely used concepts. Examples: algebra, commutative, associative, distributive laws, polynomials, factorization, solving linear and quadratic systems, geometry, congruence and similarity, Pythagorean theorem, law of sines and law of cosines, transformations, calculus / analysis, limits, continuity, derivatives and integrals, chain rule, fundamental theorem of calculus, mean value theorem. Concepts guide representation and manipulation. They're the rules of the game. 4. Mathematical manipulation, the toolkit. Manipulation is the active toolkit, how you operate on representations using concepts and domain knowledge. Elementary moves, algebraic simplification, substitution, rearrangement, factorization, cancellation. Problem-specific tools, coordinate changes, symmetry exploitation, invariance, bounding and estimation, dimensional analysis. Higher-level techniques, Fourier and Laplace transforms, linear algebraic solution methods, differential operators, optimization algorithms, generating functions, numerical approximation. Proof techniques, direct proof, contradiction, induction, constructive proofs, extremal principle, relationship, concepts, plus representation, plus domains, slash hybridics implies manipulation, the operations you perform to get results. 5. Problems. Problems are where you use manipulation to produce results. Types and examples. Single domain problems use only one branch, for example, 2 plus 2, pure arithmetic. Multi-domain problems require multiple math areas. For example, a coordinate geometry proof uses algebra and geometry. Cross-disciplinary problems extend outside mathematics. For example, modeling a population uses calculus, statistics, and biology. Polished simple examples. 2 plus 2 is a number sense arithmetic problem. X plus 2 equals 4. Mixes algebra and arithmetic. Solve by subtracting 2 from both sides to get x equals 2. Problems can be specific, hybridic, broad, or ill-defined. The classification helps pick the right representation and toolkit. Another fact, similar framework can be used to study other STEM domains with few modifications. I'll be working on that.